Bismillahirrahmanirrahim. Hello and welcome to Rahman Digital Production. This is the lecture number 92 of physics. In today's lecture, we are going to talk about linear magnification. Uh, if you remember in the last work example, that was on a piece of graph paper, we noted that the image has a height of 4 centimeter compared to the object's height of 2 centimeter. Let me show you that this is the only, if you can see that the image distance, the object distance was what, two small square, and you can see the image distance is 4 small squares. So this shows that this is a magnified image of the object and it is double. We will discuss that in a moment and will derive it as well. Let's go back to the new lecture. Okay, so we therefore say that the image is magnified, means that it is enlarged. The linear magnification, which is denoted by small m, is defined as linear magnification, which is here linear magnification. M is equal to height of the image hi divided by the height of object ho. So that is the ratio of image to the object, and whatever the result is, that will be the magnification. So let's go back to that problem, and we want to find the magnification of that figure. So linear magnification, in work example we just saw, the linear magnification is m is equal to 4 centimeter. Why 4 centimeter? Because that was the height of image, and there were 4 small squares were there, and the object was 2 centimeter of height. So when we divide 4 centimeter by 2 centimeter, we will get 2 centimeter. Okay, that was the whole story about the previous work example. Now let us do the full-fledged new example, and this is saying that the figure shows a small object of height 1.0 centimeter placed 1.5 centimeter away from a thin converging lens, and that is denoted by L, as you can see. Of the focal length is 2.0 centimeter. So let us write that O is the let me write it that O is the 1 centimeter. O dash is equal to 1 cent. It is given to us. Similarly, object distance U is given as 1.5 centimeter, and F, which is known as focal length, is also 2 centimeter. Now I made this figure for you people here, and you have to pay attention to this one. The question is saying locate the position, the size, and the characteristic of the image formed. So as you know that whenever you are drawing a ray diagram, then you have to take one line from the head of this, and then you have to bend it towards the focus point, and one line should go without any deviation from the uh, line. So as you can see that these lines will never meet, so it will not form a real image. So let us discuss that here in this example, in this figure. Yes, they also drew a line here, and then it is passing from this line, and one line is from the optical center, which is here. So whenever we want to make an image, and it is if these two rays were meeting at some point in this location, so we could write that here as well if it was in this location. So if it is not, then we have to extend this as shown in the figure by dash dash line, and they are meeting at this particular point, and you have to measure then this distance. So this will be the image of this object, and that is on the opposite side of the lens. So this sort of images are known as uh, virtual images. Why? If you are putting a screen on that location, you won't be able to see the image. The only way to see this image is from the opposite side of the lens, and through the lens you have to observe that image. But if you are not observing it through the naked eye, and you are seeing it like this, you won't be able to see this image. So this is a virtual image. The second property of this is that this is erect image. This is not inverted. That is in the same direction in which the object was there. So let us write few of the properties. We are measuring it to the scale, and when we measure it, we will be the, you can see that this is the V, the distance of the image from the optical center, and that is 6 centimeter. And if we observe the image size, then it will be image size. I am denoting it by dash, and that will be equal to 4 centimeter. The image form is upright. This is another characteristic of this object. This is upright. Another is magnified. This is a magnified image. Yes, it is. It is enlarged, and that is virtual image. Another property is virtual image. And on the same side, image is not forming on the other side of the lens on which the object is located. So on the same side of the same side of the lens of the lens behind the object. Yes, it is behind the object. So the main purpose of this work example was that how to magnify an image. In this way, a very small object can be observed in a very large size, just like we are using magnifiers. Let me define the virtual image properly. So, let us see, a virtual image is formed when the virtual rays appear to come from. Note that if screen is placed at I dash, no image can be formed on the screen, and that is what I told you. The way to observe the image is to look through the lens from the opposite side of that of the object. I told you that in this case you have to see the image from this position, that is I, and from this position you will see this image, and you will see it enlarged or magnified image. Dear students, another very important topic, and in this topic the most important things are these uh, characteristic of the converging lens. Questions are always given from the converging lens from this table. You have to understand it first. We will discuss that if the object is at the focal length, then where the image will form, and if this is the situation, what will be the characteristic of that image. Similarly, if we want to use this technique, where we can use these techniques. So let us focus on the first of the row, in which the object distance is at infinity. Remember that the object distance is always denoted by the u, and the image distance is always denoted by lowercase v. So if we want to observe an object which is far away from us, for example, there is a tree at the top of the mountain or hill, and we want to study the tree from far away. So it means that the object is at infinite distance from the lens, converging lens. Similarly, if we want to study the stars, so we will use these sort of lens, and this situation in which we are saying that the image, the object is at infinite distance. So you can see that two parallel rays, this one and this one, is coming far from away, and one line is passing from the focus point here. And you know that whenever a line is passing through the focus, after touching the lens surface, it will become parallel to the principal axis as I am showing you through this line. There are many rays coming, but we are taking the advantage of these two rays. So here it will also pass from this, and you will see that these two rays are meeting at this particular point. So we have to draw a line from here which will show the image height. So at a very large distance, if the object is of greater height, this situation will diminish the image, and that will be a smaller one, as you can see in this particular figure. One more thing, that it will be a real image, because if you place a screen at the image position, you will observe a clear cut image of that. It will be a real. And another is that it will be inverted. Here it is written, this will be inverted, this will be a real, and this will be a diminished. So image distance will be equal to f. It will, you can see that this distance is equal to the focal length as well, because that small spot is showing the focal. Both are at the same. So here we are writing that V is equal to F, and that is opposite side of the lens. The image will form. Okay, what is the use of this type of scenario? We are using this type of scenario inside the object lens of a telescope. So this type of situation, when the object is at infinity, having a very large distance, then we will use to see that through the telescope. That was the first situation. Now let us turn our focus to the second situation. First of all, let me tell you that this is 1f, this is 2f, and this is 2.5f. 2.5 or whatever. But in this case, this object is situated greater than the double of the focal length of the converging lens. The object is not placed on the focus point of the uh, uh, lens, but it is away. Then what will happen? We have to draw a line from here, and we will convert it to the first focus point, remember. Similarly, one line will go directly from here, so it will be touching each other, intersecting each other at this particular point, and then we have to draw this image line. And you can see that in this particular case, the object size is larger than the image size. So we will say that the image has been diminished, made smaller in this particular case. And that is also inverted and real and diminished. These are the property. When you understood the scenario of drawing a ray diagram, no problem will be there for you to draw this line. Now this f is between the two f. This particular statement is showing that the image distance, which is V, is between f and 2f. You can see that if it is f and this is 2f, and the image here is between the f and 2f. So remember that if the object distance is greater than 2f of the converging lens, the image will be between f and 2f, which will be real, diminished and inverted. Where we are using, that is, we are using it in camera's eyes, because your size is greater than the size of the image forming on the lens of the camera or the eye of the camera. Whenever you are printing your image on a piece of paper, so your original size is much larger than the image you are seeing on that photograph, so it will be diminished. Now the third scenario is that if we exactly place the object at 2f, if you can see it here, in the previous case it was greater than the double of the focus point, but here it is exactly, then what will happen? Let us observe that as well. So, dear students, draw array diagram, pass it through the focus point, pass one line without any deviation, and wherever they are forming, they are intersecting each other, you have to draw a line which will represent the image size as well. Very interestingly, if you see that the image is also forming on the 2f, double of the focal length, as the object is laying on the 2f as well. So it will be of the same size if you are putting the object at 2f, the image will also be at 2f, and here it is written that it is of the same size, it will be real and it will be inverted. And the image distance here it is written will be 2f, the image will be of 2f. So if you are making a photocopy of any transcript or of any document, you will see that it is of the same size it is in the document. So here this type of scenario we are using inside the photocopier making machine, and that is of equal size. In fact, you can make arrangement to diminish it or enlarge it, but by default they are of the same size, and that is quite right as well. Now next scenario is that if the object is between f and 2f. So you can see that this is the f and this is the 2f, and the image is exactly in between these 2 points. You can put it anywhere between these 2 points. It is not mandatory that put it at the middle of these 2 points. Again, one line, pass it the focal length, and one line without any deviation, make it, and now you can see that the image is inverted, real and magnified. In this case, if you are putting an object between f and 2f, then it will be magnified. You can see that this is the u and this is the v, which is image distance. So image distance will be larger from the center of the lens as compared to the object distance from the center of the lens. Now it is denoted here with V is equal to 2f, greater than 2f. You can see that 2f is here, but the image is forming at this particular position, which is greater than 2f. So that is why it is written here that it is greater than 2f. Now this is used in the projector photograph enlargement. You see that on the mobile screen or at the computer screen, the images are very small, and if you want to show those images to a group of people or employees in an office, you have to arrange the overhead projector. That overhead projector will make these small object or pictures as larger one, and in fact projectors are used to magnify the images and make them enlarge. So photograph enlargement is also, as you can see on the roadside, different panaflex images which is very large, so everybody can see it from a distance as well. So this was another scenario. Now let us turn our focus to another scenario, that if the image is exactly at the focus point of the lens, then what will happen? I am repeating it again. One line will be here, and well, remember that you have to take this distance same on the both side. It is not like this, that this distance will be larger and this, because on both sides these converging lenses are having the same focus point. So one line will be passed without any deviation, and now you can see that these two lines will never meet on the other side of the lens where the object is situated. In fact, on this side it will also not meet anywhere. So you will see the image at a very larger distance. At an infinite distance, you will see a very small image. Now that will be upright in this. This is not an inverted. If we are making it sum, that will be magnified, because this will be small and this will be very large one at a large distance, and that is virtual. Now you must understand what is virtual image, because if we place a screen at the image position, we will not be able to see that image, because it is virtual, it is not real. So that is virtual image, and I told you that image will be seen at infinity and on the same side of the object. The side on which the object is situated, the image will also be on that side, and that is mostly used in the spotlight to produce a parallel beam of light as in a spotlight. This is a special arrangement for scientific research. So if you want to see that, then you will make this arrangement. Now the final one is that if image is less than f, you can see here, let me magnify it more. So the focus point is this one, and the middle center of the lens is this one, and you can see that the object is placed between F and C. Now let us observe this scenario, that what will happen. First of all, we have to pass the line from the focus point. The second is passing it from the C without any deviation, and then we have to extend and it will meet somewhere, and then you have to draw a line at the intersection point from the principal axis. Now in this case you can see that the image is upright, the image is magnified, and the image is virtual as well. These are the three characteristics of this type of scenario. And here the image is behind the object, same side on the lens as you saw it. And this type of situation is used in magnifying glass. Dear learners, I told you that this table is of great importance if you want to see that how images are formed in converging lenses, and how we can specify different characteristics of these images. Remember that these are not that much difficult, but you have to pay full attention to these sort of question. Tomorrow is a very interesting topic, and that is application of converging lenses. That very technically where we can use these sort of lenses, very interesting. So stick to this channel for the subsequent lecture, and if you are new to this channel and haven't yet subscribed, please subscribe it and press the bell icon so that you will be informed immediately when I upload the video. Thank you for your time. Have a nice time. Allah Hafiz.